If you've been following the news or maybe just trying to figure out why your smart thermostat is arguing with you, you know that AI is no longer science fiction.
No, it's just regular life now.
Exactly.
Yeah.
But if you actually try to stop and define it, beyond all the hype, the concept can get really slippery.
Well, that's really our mission today. We've taken a deep dive into your sources here, and they cover the entire landscape of AI. I mean, everything from the philosophy that started the field decades ago, right up to the advanced systems that are trying to mimic human thought.
Right. We want to get to the core definition, understand the components that actually make these systems intelligent, and appreciate some of the really surprising challenges they face.
Especially when they try to acquire something that we take it for granted. Common sense.
So where do we even start?
You have to go back to the beginning. The field's founder, John McCarthy, he gave us the definition that really kicked everything off.
What was that?
He called it the science and engineering of making intelligent machines, especially intelligent computer programs.
Okay, simple enough. And since he coined that, AI development has really been driven by these two huge, almost contradictory goals.
That's right. Goal number one is the practical one, the immediate one. It's to create what we call expert systems.
These are the machines that help us out.
Exactly. They're designed to show intelligent behavior, but critically, they also have to be able to explain and advise and show their work to a human. They assist us.
And goal number two is the big one, the one that, generates all the blockbuster movies.
The grand philosophical one, yeah. To implement genuine human intelligence in machines. This is the hunt for systems that can truly understand, think, learn, and behave the way we do.
And this ambition, it's not new.
Not at all. But we can chart some key milestones. The idea of a manufactured person really hit the mainstream in 1923 as a play by Carol Eppek, RUR.
And that gave us the first use of the word robot in English.
It did. Then, philosophically, the groundwork was laid in 1950 by Alan Turing. He proposed the famous Turing test.
Which gave us a practical way to evaluate if a machine could actually convince a human that it was intelligent.
A very debated way, but
Yeah.
yes. And then, of course, the moment that felt like the future had just arrived, 1997.
Deep Blue versus Garry Kasparov.
The chess program defeated the reigning world champion.
That was just huge. But here's the paradox, right? Even after Deep Blue could beat the world's most complex strategic game, these incredibly advanced machines still struggle with the surprising difficulty of just being human.
It's a fundamental difference in perception. Your sources really highlight that humans perceive the world by recognizing and internalizing patterns. We are absolute masters of context.
Give us an example of that pattern recognition.
Okay, so consider a number sequence, like 40404040. A human remembers that instantly. You see the pattern 40 repeated 4 times.
Right.
A machine, though, it perceives and stores that information using a strict, explicit set of rules and raw data. It doesn't inherently get the idea of repetition or context.
And the result of that is pretty profound. I mean, we can look at a face that's half covered or a logo with a piece missing, and our brain just fills in the blank. We see the whole thing.
Machines, even today, struggle so much with that, with distortion, with missing data. If the rules don't explicitly account for that distortion, they can just fail completely.
So to replicate our thinking, AI has to conquer what? 5 core components?
That's it. Reasoning, learning, problem-solving, perception, and linguistic intelligence.
Okay, let's focus on reasoning. If machines are just fundamentally relying on these rigid rules, how do they even begin to reason?
Well, it's about structure. Your sources describe 2 main structures for it. The first is inductive reasoning, which is really the human specialty.
That's going from specific observations to a general rule.
Exactly. Every swan I have ever seen is white. Leads to the broad statement. All swans must be white. It's an educated guess.
And the second type?
Deductive reasoning. This is where machines are brilliant. It starts with general statements and applies them to reach a specific logical conclusion. The classic example is, Nita is a teacher. All teachers are studious.
Therefore, Nita is studious.
Precisely. If the general rule is true, the specific conclusion has to follow. Machines are incredible at applying known rules. They just struggle with making those broad generalizations or dealing with exceptions.
And that struggle is what led to this famous aha moment in AI research, right?
A huge one. Researchers classified AI tasks into 3 domains. You have mundane tasks, formal tasks, and expert tasks.
Mundane is the ordinary stuff, like perception, walking around. Formal is logic, geometry, and expert is things like medical diagnosis.
And the assumption at first was logical. Mundane tasks, the things we do effortlessly, walking, talking, common sense, they thought those would be the easiest to program.
But the sources say the complete opposite happened.
Exactly. Mundane tasks turned out to be far, far harder for machines than expert tasks.
Why is that? That seems so counterintuitive.
Well, it's because expert tasks, like playing chess or diagnosing a specific disease, they often rely on a really specialized, self-contained set of knowledge. The rules are clear, even if the possibilities are vast.
But mundane tasks.
They require unbelievable complexity. You need complex knowledge representation, continuous adaptation, and above all, common sense. It's just easier to code the rules for winning a chess game than it is to code the rules for knowing you shouldn't step in a puddle.
So if these systems are going to operate in the real world, with puddles and everything, they can't just be rule-based automatons. We need to talk about agents.
An agent is the technical term for really anything that perceives its environment through sensors and then acts on it through effectors.
So for a human, sensors are eyes and ears, and effectors are hands and legs.
Right. And for a robotic agent, it's cameras and motors. It's just the input-output mechanism.
And the ultimate goal is to create what's called the ideal rational agent.
That's the one. It's an agent that's capable of taking the best expected action to maximize its performance based on the history of everything it's ever perceived, its percept sequence, and its own built-in knowledge.
And imagine these agents can be pretty simple or very complex.
Oh, absolutely. At the simplest level, you have simple reflex agents. They act only based on the current moment, the current input.
Which only works if you can see everything all the time.
Which you can't.
Huh.
So the more interesting ones are the model-based reflex agents. They maintain an internal state.
And why is having an internal state or a model of the world so critical for intelligence?
Because the world isn't fully observable, and things change. A model-based agent has an internal idea of how the world evolves, and crucially, how its own actions affect that world.
Like a self-driving car.
Perfect example. It sees a wet road, that's the current percept. But its internal model knows that hitting the brake will slow the car down, even if the wet road makes it less efficient. That internal knowledge is key.
This brings us right to expert systems. These are the applications built to solve those complex problems at the level of a human expert like a doctor diagnosing a patient.
And an expert system is built on three main components. First is the knowledge base. This stores all the data, organized as if-then-else rules.
And this includes both facts and what's called heuristic knowledge.
Yeah, and that's the important part. Heuristic knowledge is the stuff you gain through trial and error. It's the accurate judgment that comes from experience.
Okay, so you have the knowledge. What's the second component?
The inference engine. That's the brain that actually manipulates the knowledge. And it uses two main reasoning strategies, and the difference is really key.
Okay.
The first is forward chaining. This one asks, what can happen next? It's a predictive model. You start with evidence and work forward to a conclusion.
Like trying to predict the stock market.
Exactly. The second strategy is backward chaining, which asks the opposite question. Why did this happen?
So that's diagnostic.
Perfect. It works backward from a known result to find the cause. This is classic diagnosis, like figuring out the specific reason for a disease.
So they can either predict the future or diagnose the past.
Depending entirely on how that inference engine is structured.
That's a great distinction. But even with all those rules, if the knowledge base is massive, how does the system find the best solution without taking forever? That's where searching comes in.
Searching is the universal problem-solving technique in AI. It's used for everything from the traveling salesman problem to solving a Rubik's Cube. And we really distinguish between brute force strategies,
which are thorough but really slow.
Hopelessly slow, often, and the more useful informed search strategies. They add problem-specific knowledge or heuristics to guide the search. They take educated shortcuts.
And the most famous example of that is the A-search algorithm.
A-star, yeah. It's brilliant because it avoids wasting time on paths that are already looking too costly.
So if I were planning a road trip, how would a search figure out the best route? Not the math, that's the logic.
Okay, think of it this way. A is constantly calculating the estimated total time of your trip. It takes the time you've already driven.
The gas I've already burned.
Right. And it adds to that an estimate of the time remaining to your destination. Best guess. By combining those two, it makes sure you don't take some silly detour that looks good for 5 minutes, but adds an hour to your trip overall.
That makes sense. But the real world is messy. The data is incomplete, ambiguous, inaccurate. That's where we need systems that can handle all that noise.
And that brings us to fuzzy logic systems, or FLS.
Right, because traditional computing is binary. It's true or false, one or zero.
Yes or no? But fuzzy logic is designed to mimic how humans reason by acknowledging the massive spectrum of possibilities in between. We don't think in absolutes. We think mostly true, a little bit cold, certainly not.
So fuzzy logic is specifically built to handle those gray areas.
Exactly. And the main benefit is that an FLS might not give you perfectly accurate reasoning, but it provides acceptable reasoning when you're dealing with uncertainty.
And that's what makes it so useful for commercial products.
Absolutely. That's why we see it everywhere. It's
Yeah.
in consumer electronics, like your hi-fi system adjusting sound based on vague inputs. It's in your washing machine.
How so?
When your washing machine detects the load is kind of dirty versus absolutely filthy, that's fuzzy logic, handling imprecise input and choosing an acceptable wash time. It just keeps machines practical.
Okay, so from ambiguous input to the infinite complexity of human communication, we get to natural language processing, or NLP.
And the goal of NLP is simple to state. Allow us to communicate with intelligent systems using natural language, like English. The difficulty, though, is profound.
Because language is just so ambiguous.
Unbelievably ambiguous. You can break it down into different levels. At the lowest level, you have lexical ambiguity, word level. The system has to figure out if board is a piece of wood, a verb, or a group of people.
Then there's syntax level ambiguity.
Sentence structure. This is the classic example. He lifted the beetle with red cap. Did he use the cap to lift it, or was the beetle wearing a cap?
And the hardest one for programmers seems to be referential ambiguity, pronouns.
It's nightmare.
Mhm.
If you say, Rima went to Gowrie, she said, I am tired. An AI has to figure out which person she refers to purely from context, which is often subtle or missing entirely.
This is why simple grammar rules don't work.
Right? The sources point out that a context-free grammar might approve a sentence that's syntactically perfect, but complete nonsense.
Like the greens peck the bird.
Exactly.
Oh,
Grammatically sound, but logically absurd. We get that instantly. A machine really struggles with that kind of absurdity,
okay, so moving from language to the physical world, we have robotics.
which is a critical application blending electrical, mechanical, and computer science. And a huge complexity here is just locomotion, getting around.
The sources highlight this energy problem. Legged locomotion, like walking, uses a ton of power and requires complex algorithms just to stay stable.
Whereas wheeled locomotion is way more power efficient and simpler to implement. But obviously it fails on rough terrain. It's a constant trade-off.
And for a robot to act intelligently, it has to see. That's computer vision.
It's the tech that allows robots to extract, analyze, and understand visual input. And its tasks are really varied. You have OCR, face detection, object recognition.
But also very specialized tasks, like estimating position.
Yeah, determining the exact location of a tumor in a human body from a scan. It's incredibly precise work.
And we see this in action in the real world.
We do. Your sources mentioned the Indian robot Daksh. It's developed by DRDO for the military, and it safely destroys life-threatening objects. It uses advanced vision and mechanics to protect human operators. It's a real-world life-saving application.
We've covered rules, logic, and handling ambiguity. Now we're at the most ambitious part of AI, the part that tries to mimic the brain itself, artificial neural networks.
Or ANNs.
Yeah.
And they're inspired by the, estimated 100 billion neurons in the human nervous system. They're made of multiple nodes or neurons connected by links. And the learning happens by changing the weights of those links.
So it strengthens or weakens connections based on experience.
That's the idea.
But that sounds incredibly complex. How do you even start to teach a network of virtual neurons? What are the strategies?
Well, we distinguish between three main learning strategies. First up is supervised learning.
This is learning with a teacher.
You can think of it that way, yeah. You give the network training data that's already labeled with the correct answer. You show it 1,000 pictures of cats, all labeled cat, and 1,000 pictures of dogs, labeled dog. It learns the pattern from the correct labels you gave it.
Okay, that makes sense, like flashcards. But what about learning without a teacher?
That's unsupervised learning. Here, there's no teacher, no pre-labeled answers. The system gets a massive pile of data and is just asked to find hidden patterns on its own,
So it might cluster customers into groups based on buying habits.
even though nobody told it what those groups should be called. It discovers the structure itself.
And finally, reinforcement learning. This is the one we hear about with games and simulations.
It's learning built entirely on observation and consequences. The system makes a move in its environment, say it's in a maze, and if the outcome is positive, It reinforces the connections that led to that move. If it's negative, it penalizes them. It learns by trial and error based on a reward signal.
Now, to handle all the uncertainty that's inherent in complex systems, especially with things like medical results, we rely on Bayesian networks.
For belief networks, yeah, they are essential. They provide a graphical structure for representing probabilistic relationships among variables. They let systems reason about an uncertain world by updating their beliefs as new evidence comes in.
So they combine what we already know with what we just saw.
Precisely. Let's take the lung cancer example. A Bayesian network combines prior knowledge, like the patient's smoking status or their pollution exposure, with new data, like a positive X-ray.
And it quantifies that relationship.
Using conditional probability tables, yes. And the network can then update the probability of lung cancer being present. It gives you a much more nuanced diagnosis than just simple deduction.
It's an incredible journey, from simple definitions to systems that replicate our brain structure. But as we wrap up, we have to talk about the unavoidable issues that come with this technology.
The speed of AI development means it poses immediate high-stakes concerns. I mean, we are fundamentally changing how society is structured.
And one of the most immediate is the threat to privacy.
Right. AI programs that can understand speech and natural language are, theoretically, capable of analyzing every email, monitoring every phone call, and creating constant, detailed digital surveillance.
Then there's the threat to human dignity, as AI takes on roles that require deep ethical judgment.
A nurse, a surgeon, a judge.
There are serious concerns about replacing humans in those fundamentally ethical positions.
And finally, the one that gets the most discussion, the threat to safety. The sources mention the danger that self-improving AI systems, if their goals aren't aligned with ours, could become so powerful they're difficult to control.
Which could lead to massive unintended consequences.
It's a necessary caution. We need to focus just as much on control and alignment as we do on innovation.
So after this entire deep dive, what should you, the learner, take away? We found that the field of AI proved that the most mundane tasks, things we do every second, like common sense, basic perception, knowing not to step on a crack, are so much more complex to program than the most expert tasks, like medical diagnosis or complex math.
And this raises a really important question. If the everyday, effortless parts of being human are the absolute hardest things for our most advanced systems to replicate, what does that incredible challenge reveal about the sheer, often invisible, structure and complexity of our own uniquely human everyday intelligence? Something to think about the next time you just walk down a busy street and navigate the world without a single logical error.